This is my geometry course. Today we're going to learn points of concurrency generated by triangles. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. The material that we're going to cover today is not really a very important part of the geometry curriculum. In fact, many teachers actually skip this material altogether. I think there's two reasons that they often skip the material. Number one, you're not really going to see these concepts in upper math courses or entrance exams. And number two, it's very difficult to write problems for these concepts. So teachers just like to skip this stuff altogether. But nonetheless, this is a part of the geometry curriculum. And if you take a test that evaluates your knowledge of the geometry curriculum, you may see this material. So we're going to learn it. And in the next class, or possibly this class if we have time, we're going to use this material to review your knowledge of linear equations, which you learned in my previous course, Beginning Algebra. So all that said, let's get started. We're going to start with something that is review for you, perpendicular bisectors. But we are going to apply perpendicular bisectors to triangles. If you consider the side of a triangle to be a segment, then each side of a triangle has a perpendicular bisector. In this example, you see we have a perpendicular bisector, and this side would have a perpendicular bisector, and this side would also have a perpendicular bisector. So again, there are three perpendicular bisectors for each triangle because there's three sides of a triangle. And again, this is a bisector because this length is equal to this length. And we have a 90-degree angle, so that's why it's perpendicular. Now, we also learned about angle bisectors. This is an angle bisector because it cuts this angle in half. And there are three angles in every triangle, so obviously there are three angle bisectors in every triangle. So we have 1, 2, 3. This is just an example of one of them. But we're going to learn something new. We're going to learn something called a median. A median is a segment that starts at a vertex of a triangle and goes to the midpoint of the opposite side. And it's important to understand a median is only a segment. So this is the median for that side, and we have another median start at this corner and go to the midpoint of that side. That's a second median. And we have a third median start at this corner and go to the midpoint. It's supposed to be a segment, straight segment there. So there are three medians for every triangle. And don't worry, I'm going to go back to all these and give you a chance to take a screenshot. The last special ray or segment or line that we're going to talk about are altitudes. Altitude is just the height of the triangle. So if you set a triangle on for example, this triangle, if you set it on the green side, we then call the green side the base because it's at the bottom. And the altitude, this orange segment, is the height because it goes up to the top vertex. And it's perpendicular. It must be perpendicular. Now, if you set the triangle on the blue side now becomes the base, and the distance from the top vertex down to the extended base over here, that is the altitude. Again, if you just consider this base to be the ground, then you extend that ground out past here because the altitude has to go from the top to the ground. So this is a case where the altitude is actually outside the triangle, and then of course if you set it on the purple base, you have the same situation. So there are three altitudes for each triangle. Now I want you to be aware that we're oftentimes considering lines, segments, or rays that contain the altitude. What I mean by that is we might have a line that goes it extends beyond the altitude, but the altitude is inside the line. So I know it's a little confusing to think of it that way, but go ahead and take screenshots of these special lines, rays, or segments. So be sure and get a screenshot of that because I don't want to have to go back to it. And we're now going to do some practice. So it says, identify the line, ray, or segment as a perpendicular bisector, PB, angle bisector, AB, median, M, or line or ray or segment containing the altitude. So I'm going to do this first one for you. You can do it along with me if you want, but I'm going to do this first one, then I'm going to give you a problem on your own. So the first one, we start at a vertex and go to the midpoint of the opposite side. So that is a median. That's just the definition of a median. And I know it's the midpoint because these lengths are equal. Now the second one is we have an angle that is bisected, is cut in half to 25 degrees and 25 degrees, so that would be an angle bisector, AB. And over here we have a perpendicular bisector, PB, because it's perpendicular and it bisects this side. So again, the whole point of this is just to get used to these special lines, rays, or segments. And in this case, we have a ray that contains the altitude, because if you consider this to be the base, then this would be the top. It's upside down, but this would be the top, and it goes all the way through, and it's perpendicular to that segment that's extended from the base. So that's an altitude, or it contains the altitude. Now I forgot something here. In this case, this isn't actually a special case. That's a perpendicular bisector, but it's also a line that contains the altitude. So we'll say and altitude, because it goes through. It goes from the top. If you consider this to be the base, this will be the top vertex. It goes from the top vertex to the base, and it's perpendicular to the base. So it must be an altitude, or it contains the altitude. Now, you might be thinking, well, what about a median? Isn't this a median? It would be a median if it were just a segment. If it were just this long, segments have to be, or medians have to be segments. So I'm not going to call that a median, even though it looks like it would be. I know that's kind of confusing, but again, as long as you get the general idea of this stuff, it's okay. We don't need to nitpick. Number 5, that is a perpendicular bisector. And we have an angle bisector, because it cuts this angle in half. And we have a perpendicular bisector again. And that is not an altitude because it doesn't hit this vertex here. And then we have an altitude here. That's an actual altitude. It doesn't just contain the altitude. It is the actual altitude, because it starts at the vertex and stops at the line extended from the base. All right, so hopefully you're getting the idea here. So now it's time for you to try. Go ahead and try number 2. And remember, I'm going to give you one more opportunity to take a screenshot of those things, because you're going to need this whole page here to do these problems. So try number 2. When you come back, we'll do it together. All right, we're back. If you said perpendicular bisector, you're correct. It's perpendicular. It has the red box, and it bisects this side because this length is equal to this side length. And over here we have a median. If you said median, good job, because it bisects this side, and it goes all right, so go ahead and try number 2, and when you come back, we'll do it together. All right, we're back. This is a perpendicular bisector, because it has this red box here, meaning a right angle, and these lengths are the same. And over here we have a median, because it bisects this side and it comes from the opposite vertex of that side. So if you got those answers, good job. And this one's kind of a tricky one. This would be containing an altitude, so ALT. The ray itself is not the altitude. The altitude only goes, it's only a segment. An altitude is really only a segment, but it contains the altitude. So we say ALT. And Number 4, and by the way, it's an altitude because if you go from the top all the way to the base and it's perpendicular to the base, meaning we have a red box there, then we know it's an altitude. So that was kind of a tricky one. This is an angle bisector. And we have an altitude. That's an actual altitude there, not just containing the altitude. And we have a median. This is containing an altitude. It is not a perpendicular bisector because this length is not equal to this length. And it's not a median for the same reason. And here we have an altitude because it's starting from a top vertex and it goes down to a segment that extends from the base and it's perpendicular. So if you got those answers, good job. That was just necessary to learn to go over all that stuff because we're going to use it as we go along in this class. But before we proceed, we're going to have to learn about concurrent lines, rays, or segments. Lines are concurrent when there are 3 or more of them that intersect at a common point. So these are concurrent lines because there's 3 of them. You can't have concurrent lines if there's only 1 or 2 of them. You have to have at least 3. These are concurrent because they all meet at the same point, this red dot here. These are concurrent rays because they all meet at the same point, this dot here. These are concurrent segments. These are not concurrent because they don't meet at the same point, and these are not concurrent, and so on and so forth. That special point is called, the point where they meet is called the point of concurrency. So let's go ahead and get a screenshot of all that. And now we're going to do some practice problems. The concurrency is really easy. We're just studying it because we're going to need it for the rest of the class. So number 3, which lines are concurrent? You may select more than one group. So let's see. It looks like, what do you think? Which ones are concurrent? If you said 2, you're correct. Let's try number 4. Which rays are concurrent? So try number 4. Which groups do you think have concurrent lines? Or actually concurrent rays, excuse me. If you said this one and this one, you're correct. So that's just some practice with concurrency. So now we're going to get to the heart of this class, and that is points of concurrency generated by special lines, rays, or segments of triangles. We're going to learn 4 theorems. The first theorem is the Circumcenter Theorem, and I'm going to give you a chance to take screenshots of all these theorems, so don't worry about it. If you draw all of the perpendicular bisectors, here's a perpendicular bisector, here's a perpendicular bisector, here's a perpendicular bisector. If you draw all those perpendicular bisectors, it turns out that they're concurrent. What that means is they meet at the same point, and that just happens to be that little blue dot there. This one, and this one, they all meet at that blue dot. So that is the Circumcenter Theorem. It says that those perpendicular bisectors of triangles are concurrent, and that point has a special name. It's called the circumcenter. And there's 3 things to know that those perpendicular bisectors are concurrent, number 1. Number 2, the point of concurrency is called the circumcenter. And the last thing that we haven't talked about yet is that the distance from that point of concurrency, the circumcenter, to the vertices of the triangle, that distance is the same for all the vertices. So that's the purple line, or purple segment. This length is equal to this length is equal to this length. So that's what the Circumcenter Theorem tells us. The distance from the circumcenter to the vertices, this distance, and this distance, they're all going to the vertices of the triangle. those distances are all the same. That's the Circumcenter Theorem. And I know what you're thinking. You're thinking, who cares? Well, we're going to do practice problems with these later on. That's the Circumcenter Theorem. That was based on perpendicular bisectors. Now we're going to the Incenter Theorem, which uses angle bisectors. Now if you draw all the angle bisectors, then the Incenter Theorem tells us that those angle bisectors are concurrent. They all meet at the same point, this blue dot again. So those angle bisectors of any triangle, they're concurrent, and that point of concurrency is called the incenter. And the distance from the incenter to the sides of the triangle, those distances are all equal. So one way to say it is the incenter is equidistant from the sides of the triangle. So those distances, those purple distances, they're all the same. They're all equal. The shortest distance from a point to a line is a segment that is perpendicular. That's why we have these red boxes. That is the Incenter Theorem. So three things to know. Number one, the angle bisectors of triangles are concurrent. Number two, the point of concurrency is called the incenter. And number three, the incenter is equidistant from the sides of the triangle. So the orange rays are the angle bisectors, and the purple segments are the distances from the incenter to the sides of the triangle. Now we're going to learn the Centroid Theorem, and of course the centroid uses medians. So these orange segments are the medians of the triangle. They go from a vertex to the midpoint of the opposite side. And there's three things to know about the Centroid Theorem. Number one, the medians are, you guessed it, concurrent, meaning they meet at the same point. And that point is called the centroid. That's the second thing we need to know. And the third thing we need to know is that the distance from a corner, from a vertex to the centroid, is 2/3 the length of the median. Now I know that seems kind of confusing, but all that means is if this distance is 2x, then this distance is just x. It's half that distance. And if you don't understand that, that's okay. We're going to do practice problems, and you're going to figure out exactly what that or how that applies. The last theorem is the Orthocenter Theorem, and that's based on altitudes, or lines containing altitudes. In the Orthocenter Theorem, there's only two things you have to know. Number one, the lines containing the altitudes are concurrent, and the point of concurrency is called the orthocenter. So that's all you have to know for that one. Now, I know that's a lot to learn there, but let's go ahead and take screenshots of all that. Get a screenshot of that page, and get a screenshot of the Orthocenter Theorem. And I want you to be aware that the incenter and the centroid are always in the center, or they're always inside the triangle. But I want you to be aware that sometimes the circumcenter and the orthocenter are outside the triangle, as you can see, or sometimes they're on the triangle. But anyway, let's do some practice problems. So we're going to start with the Circumcenter Theorem. We're not going to do all the theorems at once, because I know what you're thinking. You're thinking this is too much to take in at once. So we're just going to take it theorem by theorem here. So we're going to do the Circumcenter Theorem first. Let's see here. If point L is the circumcenter of each triangle below, find the quantities listed. So we're going to do these problems together, so don't worry about it. You're going to get the idea of what the Circumcenter Theorem is. We have a triangle here, and they want us to find the length of CD. And we're going to use the Circumcenter Theorem to do that. So let's see, where is CD? This is CD here. And we're told that point L is the circumcenter. If point L is the circumcenter, and we see that these angles are 90 degrees, then that means that these orange segments must be perpendicular bisectors. They must be perpendicular bisectors because they go through the circumcenter, and they're perpendicular to the side. So we don't have to give a formal proof of that. You can just kind of assume that those are perpendicular bisectors. So if they're perpendicular bisectors, that means that this segment bisects this side, which means that if DA is 4.5, then DC must be 4.5 also. So that's just based on the definition of perpendicular bisectors. FB, same situation over here. If AF is 4, then FB must be 4 also. Because again, this is a perpendicular bisector, so it bisects this side. AL is the distance from here to here. And this is where we need the Circumcenter Theorem. Now we know this is the circumcenter, and the Circumcenter Theorem, one of the things it tells us is that the distance from the circumcenter to the vertices is the same for all vertices. So these distances are the same, and this distance is the same. So if this distance from this vertex to the circumcenter is 5, that means the distance from the circumcenter to this vertex is also 5. So AL is 5. So again, we're using the Circumcenter Theorem. Now we need to find LF. LF is this distance here. Now we just showed, what we're going to do is we're going to use this triangle. All right, so I'm going to pull that triangle out. And we know that this is a 90-degree angle, obviously, because this is a 90-degree angle. And we just showed that this side, AL, is, I'm going to write those letters out so we know what we're talking about. AL we just showed is 5. And AF is 4, we know, so we have to find LF. We have to find this side, which we can, I guess we can call it X. So in order to find that side, we have to use the Pythagorean theorem. And the reason we can use the Pythagorean theorem is because we have a right triangle. Remember, you cannot use the Pythagorean theorem unless you have a right triangle. Let me write this out here. So remember, the Pythagorean theorem is a squared plus b squared equals c squared. So a squared we can make 4, b squared we can make x, and c we can make 5. So now we have 25 is equal to x squared plus 16. Subtract 16 from both sides and you get x squared is equal to 9. And then x is equal to 3 if we square root both sides. So LF is equal to 3. This is an example where the circumcenter is actually outside the triangle. We're looking for FB. We know that FG is 9 millimeters, and again, the same logic. We're told that point L is the circumcenter. So if we know point L is the circumcenter, and we know that these segments are going through the circumcenter and they're perpendicular to the sides because of those red boxes, we know that these are perpendicular bisectors, these orange segments. So that means if this length is 9, this length must be 9 also. So FB is 9 millimeters. So this is really easy stuff, pretty much. You are going to have to use the Pythagorean theorem for some of these problems, but a lot of them are really, really easy. You just look at the picture and you know the answer immediately. CE, again, same situation. If EB is 7 millimeters, then CE must be 7 millimeters also because, again, those orange segments are perpendicular bisectors. We don't need a formal proof to show that they're perpendicular bisectors. I'm not going to require you to do that. Because this is a circumcenter, point L is a circumcenter, the Circumcenter Theorem tells us that the distance from the circumcenter to the vertices is the same for all vertices. So if this length, the distance from the circumcenter to this vertex is 11 millimeters. That means LB, the distance to the other vertex, must also be 11 millimeters. So very easy. And FL is this little distance here, that little distance right there. And for this one, it looks like we're going to have to use a right triangle again. So I'm going to pull that triangle out. And this is F, and this is L, and this is G. And we know that GF is 9 millimeters, and we know that GL is 11 millimeters, and we're looking for FL. We'll call that X. So we're going to use the Pythagorean theorem again. We have 9 squared plus x squared equals 11 squared. 9 squared is 81. 11 squared is 121. So now we have x squared, subtract 81 from both sides, and we get x squared is equal to 40. Square root both sides, and we get 2 root 10. Now I'm not going to demonstrate how to pull a perfect square out of a root or anything like that. Again, I expect you to know that by now. If you don't, you can always go back to my beginning algebra course. But that would be 2 root 10. So we say 2 root 10 millimeters. Again, if you need practice with the Pythagorean theorem, how to pull a perfect square out of a root, you can go to my Pythagorean theorem class. All right, so now hopefully, you can take screenshots of those problems that we just did if you want. And again, if you didn't get a screenshot of the Circumcenter Theorem, be sure to do that. And now it's time for you to try. So now the circumcenter is inside. Sorry, my computer's jumping around. Now the circumcenter is inside the triangle, L here. And remember, the Circumcenter Theorem tells us that the distance from the circumcenter to each vertex is the same for all vertices. And you might have to use the Pythagorean theorem. And why do we know that these are perpendicular bisectors? Well, because they go through the circumcenter. We're told that L is the circumcenter, and they're perpendicular to the sides because of these red boxes. So go ahead and try number 7, and when you come back, we'll do it together. All right, we're back. We know that they're the orange segments are perpendicular bisectors, so we know DC has to be 12 because AD is 12. LC, we know LC has to be 13. How do we know that? Well, we know LC is 13 because AL is 13. Remember, that's what the Circumcenter Theorem tells us. The distance from here to here is equal to the distance from here to here. The distance from the circumcenter to the vertex is equal for all vertices. The distance from here to here will be also 13. FB. FB, that's going to be 11. So we have another easy problem there. Whoops. So that is 11. Because this is 11 and this is 11. Again, they're perpendicular bisectors. Now LD. LD is this distance. And we're going to have to use this triangle here. So I'm going to pull that triangle out. I'll try to put it down here, I guess. Now it's kind of a crappy triangle. There we go. Now we know that this angle is 90 degrees, so this angle must be 90 degrees also based on the concepts that we learned previously in this course. So we know this side is 12 and this side is 13, and we're looking for X. So we can use the Pythagorean theorem. 12 squared plus x squared equals 13 squared. Now remember, you got to know where to put that variable. Sometimes it goes on this side, sometimes it goes, it's by itself on one side. It depends on if it's the hypotenuse. Remember, the hypotenuse is always opposite the 90-degree angle. So the hypotenuse always goes by itself. So we have 144 plus x squared equals 169. Subtract 144 from both sides, and we get 25. Square root both sides, and we get x is equal to 5. So LD is equal to 5. So if you got those answers, good job. If you didn't get those answers, that's okay. Just figure out what you did wrong. All right, on to number 8. Now remember, point L, we're told that's the circumcenter. So because it's the circumcenter, and because these segments are going, these orange segments are going through the circumcenter and they're perpendicular to the sides, that means these orange segments must be perpendicular bisectors. They must be. And this one here is a perpendicular bisector because we have that little dotted box. So this is going to be a more difficult, or not a more difficult, but it's just kind of a strange problem because the circumcenter actually is on the triangle. So the distance from the circumcenter to the vertex is actually part of the the length is actually on the triangle. So try number 8. If you get stuck, that's okay. But be sure to attempt this problem. Pause the video. When you come back, we'll do it together. All right, we're back. LC. Because this is a perpendicular bisector, it bisects, which means because this length is 17, this length must be 17 also. So LC is 17. And BL. BL is the distance from the circumcenter to a vertex, but we already know that the distance from a circumcenter to a vertex is 17, and the Circumcenter Theorem tells us that those distances are all the same. This is 17, this is 17. Let me get my highlighter out. This is 17, this is 17, and this is 17. That's just part of the Circumcenter Theorem. So BL is 17. AD, again, we have a perpendicular bisector here. Actually, I guess that doesn't really help us because we don't know either of these lengths here. But we do know that this length is 15 and this length is 17, and we know that because this angle is 90, this angle must be 90 also, so we have a right triangle. So we can take that triangle out, and I'll put it over here. We have ADL. This is 17 and this is 15, so we're looking for x. Use the Pythagorean theorem, and we have x squared plus 15 squared is equal to 17 squared. X squared plus 225 is equal to 289, I believe. Subtract 225 from both sides, and you get 64. And therefore, square root both sides, and x is equal to 8. So AD is equal to 8. Now DB, if AD is equal to 8, that means DB must be equal to 8 also, because again, this is a perpendicular bisector. So DB is also equal to 8. So if you got those answers, good job. Again, that was a strange one because the circumcenter actually landed right on the triangle, one of the sides of the triangle. All right, so that was the Circumcenter Theorem. We use the Circumcenter Theorem quite a bit. Now we're going to use the Incenter Theorem. That's where you use angle bisectors. So get a screenshot of this if you haven't already got a screenshot. So we're told point M is the incenter. That's where all the angle bisectors meet. So point M is the insector of each triangle, and it wants us to find the quantities listed. So same type of problem, except we're dealing with angle bisectors now. Because this segment extends from the vertex to the incenter, we know that it must be an angle bisector. So this angle must be equal to this angle. Same thing with the other segment. it extends from a vertex to the incenter, so this angle must be equal to this angle. And I think that's what they're looking for. They're looking for the measure of angle MBC. It's kind of hard to see, but that's this angle in here. So that angle is the same as 55 here because it's an angle bisector. So that is 55 degrees. I hope you can see that. So we're kind of using the converse, so to speak, but we're not really doing formal proofs of that. It's pretty much, I'm just allowing you to assume that. So now we're looking for MJ. Now remember, the Incenter Theorem tells us that the incenter is equidistant from the sides of the triangle, and because these red boxes are here, that means that these blue segments represent the shortest distance from the incenter to the sides of the triangle, and they're equidistant, or they're all equal. So if this length is 5, that means this length must be 5 also. So MJ is equal to 5 feet. Now we want the measure of angle MAJ. That's this angle here. Okay, but we don't know anything about this angle, or especially not this angle. But we do know this angle is 24.8, and if we add up 55, if we multiply 55 times 2, we can figure out this whole angle, angle B. Then we can use the angle sum theorem, or excuse me, the triangle sum theorem that we learned in a previous class. And then we can just find this total angle and then divide it by 2, because again, we know that this is an angle bisector. So I know that's a lot to think about, but let's go ahead and write it out. So the measure of angle A plus the measure of angle B plus the measure of angle C has to be equal to 180. Again, remember, we learned that. We learned that theorem. So measure of angle A, we don't know. That's what we're looking for. Plus the measure of angle B, which is 2 times 55, because remember, 55 is half of that angle. And the measure of angle C is 24.8. That equals 180. So 2 times 55 is 110. Add that to 24.8 and you have 134.8. And subtract 134.8. And we really don't have much room here, but you can use a calculator if you want. 180 minus 134.8 is 45.2. So the measure of angle A is 45.2. And now so we found this angle here using the triangle sum theorem. But now we need to find the measure of angle MAJ, which is this angle here, which is half of that angle, because again, this is an angle bisector. So we need to take that angle, measure of angle MAJ is equal to that angle we found, 45.2, divided by 2. And let's see what that would be. Divided by 2 equals 22.6 degrees. So that is the answer to that one. So as you can see, we're just using the theorems, and it's kind of like a maze. We're trying to work our way through the maze. So 22.6. Now we just need to find AM. To find AM, we're going to need to pull out this triangle. It's a right triangle. And we know that this side is 5. We already found that side. That's MJ. And we know this side is 12, so we just need to find the hypotenuse. So we use the Pythagorean theorem, 12 squared plus 5 squared equals x squared, and do all the math on that, and you get x is equal to 13. So AM is equal to 13 feet. So again, we're using the Incenter Theorem. All right, on to number 10. We're going to do one more of these together before you try one on your own. Measure of angle MAC. So MAC is this angle here. Now again, we're told that M is the incenter. That's the special point of concurrency. Because this segment, this orange segment, goes from a vertex to the incenter, that means that this segment must be an angle bisector. So if this angle is 37, this angle must be 37 also. So it equals 37 degrees. Sorry, my computer's kind of, I don't know what this program is doing, but it's making my writing really sloppy. So now measure of angle MCD. So that's this angle over here. But we don't know anything about these angles. We do know that this angle is 30, and we know that this angle is 37 times 2. And so it looks like we can use the triangle sum theorem again. So the measure of angle B, actually I probably just do alphabetical order. That measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. Measure of angle A is 2 times 37. Measure of angle B is 30. And measure of angle C we don't know. So now just do all the math on that. And looks like we get 76 degrees. So measure of angle C is 76 degrees. Just double checking that math. So we found the measure of angle C, which is this entire angle, but we don't want the whole angle. We just want DCB. Actually, wait a second. We do want the whole angle. Oh, sorry about that. Wait, no, we're on part B. Sorry, I thought I was on part C. We want MCD. So that's this angle here. And that's going to be measure of angle MCD is going to be 76 divided by 2, which is 38 degrees. So that is 38 degrees. And now DCB, that's the entire angle over here, so that would be 76. We already found that. I don't know what my computer's doing here, making my writing so sloppy. AM, we're going to have to use the Pythagorean theorem and the Incenter theorem. Now remember, the Incenter theorem tells us that the incenter is equidistant from the sides of the triangle. So this distance, because there's a right angle, we know that's the distance from the incenter to the side of the triangle, and this is also the distance from the incenter to the side of the triangle. So because this is 3 inches, this must be 3 inches also. So AM, actually we can't find AM yet. I gotta pull out that right triangle. We're partway there. We know this is a right angle there, because it says a right angle, and this is 3 inches, this is 4 inches, and we're looking for AM. So again, this is A, this is M, and this is D. So now we use the Pythagorean theorem. And it doesn't look like we have a lot of room here, so I might have to kind of skip ahead. But if you use the Pythagorean theorem, we have 3 squared plus 4 squared equals x squared. X is then equal to 5. So AM is equal to 5 inches. So we did 2 problems on the incenter. Now it's time for you to try one on your own. You can take a screenshot of those problems that we just did with the incenter. And you can also take a screenshot of the Incenter Theorem if you haven't done that already. If you've already taken screenshots, I'm sorry that I keep pulling you back here, but I don't want you to get stuck if you didn't do that. So now try number 11, and I'll keep number 10 in the window there. Again, this problem is telling us that M is the incenter. And if M is the incenter, then that means that these orange segments are angle bisectors. They have to be angle bisectors because they extend from the corners of the triangle to the incenter. So by definition, they must be, or not necessarily definition, but we can prove. I'm not going to make you prove, but we can prove that those are angle bisectors. So go ahead and try number 11, and when you come back, we'll do it together. All right, we're back. Measure of angle MBC. Well, we know that this angle here is 45. So because MB is an angle bisector, that must be 45 degrees also. So if you got that answer, good job. Measure of angle MAB. That's this angle here, but we don't know anything about that angle. We know that this angle is 20, and this angle is 45 times 2, so we can find this angle and then divide by 2 because this is an angle bisector. So that's a lot of work. So we're going to use the triangle sum theorem. Measure of angle A plus measure of angle B plus measure of angle C is equal to 180. And measure of angle C is 20 degrees. Measure of angle B is 45 times 2. And we don't know measure of angle A. Do all the math on that. And we get measure of angle A is 70 degrees. But we don't want the measure of angle A. We want the measure of angle MAB. We want this angle here. We found the entire angle, but we want this angle, so we just divide it by 2. Because again, that's the AM is an angle bisector. So the measure of angle MAB is equal to 70 divided by 2, which is 35 degrees. So 35 degrees. Measure of angle CAB. We already found that. That's the entire angle here. So that would be 70. And we're looking for AD. Now we know that MD is 6 because this length is 6. That's the Incenter Theorem. So I'm going to pull out that triangle, and that's a right triangle. And this side is 6. This side is 10. And we're looking for X. So we use the Pythagorean theorem. X squared plus 6 squared is equal to 10 squared. And do all the math on that, and we end up with X is equal to 8. So AD is equal to 8. If you got 8, good job. All right, so if you got those answers, very good. Now we're going to go on to another incenter problem. Go ahead and try number 12. Now remember, we're told in this problem that M is the incenter. We know it's the incenter. They told us it's the incenter. So we can assume that it's the incenter. And because these segments are coming from the vertices, these orange segments, they must be angle bisectors because they start from a vertex and they go to the incenter. We're told M is the incenter, so they must be angle bisectors. So try number 12, and when you come back, we'll do it together. All right, we're back. Measure of angle BCM. That's this angle here, which must be 37 because this angle is 37, because that orange segment is an angle bisector. Measure of angle ABM. We don't know anything about these angles, but we can use the angle sum theorem like we did previously. Measure of angle A plus measure of angle B. All the angles in a triangle, they always add up to 180. Plus measure of angle C is equal to 180 degrees. Measure of angle A is 60 degrees. Measure of angle B, we don't know. And measure of angle C is 37 times 2. I'm going to write that more legibly. And so do all the math on that, and we get 46 degrees. Now that's the entire angle. We're not looking for the entire angle at B. We just want ABM. So ABM is this angle, so we have to divide it by 2 because this segment is an angle bisector. So the measure of angle ABM is equal to 46 divided by 2, which is 23 degrees. So 23 degrees for that one. So if you got that answer, good job. And measure of angle ABC, that's the entire angle at B. So that would just be 46 degrees. And BM, as usual, we're going to have to use a right triangle. Now, we have to use the Incenter Theorem also, so we know this length is 5, so this length must be 5 also. And I'm going to take that triangle out so we can see what we're dealing with. And I'm going to need to label that. I'm just going to label it D. So we know that this side is 5. We know this side is 12, and we'll call this side x, because we're looking for BM. So we can use a Pythagorean theorem. X squared equals 12 squared plus 5 squared, and do all the math on that. And we end up with x is equal to 13. So BM is equal to 13. So if you got that answer, good job. So we learned how to use the Circumcenter Theorem and how to use the Incenter Theorem. Now we're going to learn how to use the Centroid Theorem. So if you haven't got a screenshot of that Centroid Theorem, be sure to do that. There's no use in doing these problems unless you have that theorem right in front of you. And so let's attempt number 13 now. If the segments below, the orange segments that is, if the segments below are the medians of the triangles, find the quantities listed. So this segment is a median, this segment is a median, and this segment is a median. And we can see that because they're all medians, they intersect at the same point, and that point is the centroid. That's the centroid theorem. So now we're looking for GD. We want to know the length of GD. So GD is this length. That's really easy because these are medians. They start at a vertex and they hit the midpoint of the opposite side. So if this side is 10, this side must be 10 also. That's really easy. GA. Now what is GA? Now we're going to have to use the centroid theorem. Now the centroid theorem says that the distance from a vertex to the centroid, which is A, is 2/3 the length of the entire median. So I know that sounds kind of complicated, so let me just explain. All that means is the distance from the vertex to the centroid is double the distance from the centroid to the midpoint of that same median. The midpoint of this side regarding that median. So all that means is that GA is just twice AE, so 2 times 8. So it's equal to 2 times 8, which is 16. That's the centroid theorem. And if that's a little complicated, that's okay. We're going to do more problems, so you'll see how this works. DA, we have another median here. The distance from the corner, from the vertex to the centroid, is 2/3 the distance of the whole median. So that means that this represents 2/3 and this is 1/3. So 1/3 is half of 2/3, so you just take 12 and divide it by 2, and that gives you dA. Again, I know that seems a little complicated, but that's the centroid theorem, so 6 is dA. GB is this distance down here, and that's going to be really easy because this is a median, which means it goes to the midpoint. This is the midpoint of this side. So if that's the midpoint, that means this length is equal to this length. So FB GB, that's just 13 plus 13 is equal to 26. And there you go, 26. All right, so let's try another one together before you try one on your own. And keep in mind, these centroids are always in the middle, or they're always inside the triangles. They're never on the triangles or outside the triangles. So we're told that the orange segments are medians. So because they intersect here, that must be the centroid. AE is 12 because, again, these are medians, so that's the midpoint. So if this is 12, this must be 12 also. GD, we know that this length here is 14. So according to the centroid theorem, this length must be half of 14. So equals 14 divided by 2, which is 7. Now AB is this length. And we know that because these are medians, this length must be equal to this length. So we just add 11 to itself, and we get 22. Part D, if FC is 15, so this whole length here, if that's 15, then what is DC, this length? So what we need to do is we need to break these into thirds. So this is 1/3 of the length, and we have 1/3 of the length here, and we have 1/3 of the length here. So the total length is 15. So if we divide it by 3, 15 divided by 3 equals 5 is 1/3 the length of the median. So 5 is 1/3 the length of the median, and we're looking for DC, and DC is 2/3 the length, so that's 5 plus 5 is 10. So DC is 5 plus 5, which is 10. All right. So on to the next problem here. Now it's time for you to try one. We've done 2 centroid problems, and you can take a screenshot of these if you want. These 2 centroid problems we did. Remember, we're told that these orange segments are medians, so because they intersect at this point, that must be the centroid. And so we can use the centroid theorem. So try number 15. And when you come back, we'll do it together. All right, we're back. AD is 46 because this length is 46. That's just based on the definition of median. So AD is 46 centimeters. BC, This length is 22, and therefore by the definition of a median this length must be 22 also. So BC is 2 times 22, which is 44 centimeters. So we're just getting used to what medians are and what angle bisectors are and what perpendicular bisectors are and so on and so forth. Let's see, BF. FD is 1/3 of the length of the median, and BF is 2/3. 2/3 is just twice 1/3, so 2 times 13 is equal to 26 centimeters. So if you got 26 centimeters, good job. AE, that's the total length here. So this length represents 2/3, and this length represents 1/3. So take 2/3 divided by 2, that's 24. This length would be 24. So we have, let's see, 48 plus 24 is 72 centimeters. I'm going to move this A over a little bit. 72 centimeters. So if you got those answers, good job. Now we're going to go to our last centroid problem before we do the last type of problem. Go ahead and try number 16. Remember, we're told that those orange segments are medians. So they must intersect at that centroid, that light blue dot. So try number 16, and when you come back, we'll do it together. All right, we're back. DF, that's 1/3 the total length, and this is 2/3 the total length. So that would just be 6 divided by 2 is 3. AC, this length is 4. So this length must also be 4 based on the definition of the median, because it bisects it goes to the midpoint. So AC is just 4 plus 4, which is 8. So we got those answers, good job. GB, same situation. GB must be 5 because these are medians. They go to the midpoint of the sides. So this side is 5, therefore this side must be 5 also. Let's see here. Waiting for my computer to catch up there. All right, so now if AE equals 6, if this whole median length equals 6, then what is DE? Well, DE is 1/3 of the total median length. So we just have to find 1/3 of 6. So if you divide 6 into 3 parts, each part is 2. So that would mean DE is 2. It's just 6 divided by 3 equals 2. So if you got those answers, good job. All right, so now we're going on to the Orthocenter Theorem. It says if point D is the orthocenter of each triangle below, find the quantities listed. Now remember, the Orthocenter Theorem, I don't know if we talked about this, but the Orthocenter Theorem, I think we mentioned this, it doesn't really say much. It really just says that the lines or segments or rays containing the altitudes are concurrent, and the point of concurrency is called the orthocenter. That's all it really says. But we're still going to do practice problems to get used to this idea of concurrency. So we'll do these first couple problems together. Notice the orthocenter is outside the triangle. Orthocenters can be outside the triangle, on the triangle, or in the triangle. So now we're looking for the measure of angle ACD. So that's this angle here. Now, pay attention to this. This is going to be kind of weird. This segment is going through the orthocenter. We're told that D is the orthocenter, right? And it's also going through a corner, a vertex of the triangle. So because it's going through the orthocenter and a vertex, that means that this angle here must be 90 degrees. Because that must be a segment containing the altitude, because the altitudes always go through the orthocenter and they always go through a corner of the triangle, and they're always perpendicular to the side opposite that corner. So this angle must be 90 degrees. So the measure of ACD is 90 degrees. I know that seems like a lot of weird stuff, but we can just assume that without really proving it. Again, you're getting used to the idea of altitudes here. So now the measure of angle AEC, that's this angle here. We know that this angle is 30, and we know this angle is 90, so we can find this angle with the triangle sum theorem. So I'm going to pull that triangle out. It's not a very good triangle there. Doesn't have to be perfect. So this is a right angle, and this angle is 30 degrees. That's A, E, and C, and we're looking for this angle, which we could call X, or whatever you want to call it. I guess we can just call it the measure of angle E. So the measure of angle A plus the measure of angle E plus the measure of angle C is equal to 180 degrees. So that's the triangle sum theorem. Measure of angle A is 30. Measure of angle E we don't know. And measure of angle C is 90. Do all the math on that, and we end up with measure of angle E is equal to 60 degrees. So that is AEC, 60 degrees. Now we need to find the length of CD. Now we know that this side is 1 and this side is 2, and we see we have a right triangle there. If this is a 90-degree angle, then this must be a 90-degree angle. So we can take this triangle out. Let me highlight that to show you what triangle we're using. We're going to take this triangle out. I'm going to put it over here. We have 1, 2, and we're looking for this distance here. So that's C, D, and B. It's kind of confusing sometimes to see what triangles we're looking at. So now we need to use the Pythagorean theorem, x squared, and again this is a right angle, x squared plus 1 squared is equal to 2 squared. Do all the math on that, and we end up with x is equal to square root of 3. So CD is the square root of 3. And we have to write millimeters. Let me move this over a little bit. So that is millimeters, and rectangle that answer. Now the measure of angle DCB, that's this angle here, which we already talked about. That is 90 degrees. All right, so that was our first orthocenter problem. Again, we're not really using much with the orthocenter theorem. We're just studying altitudes. So let's try one more of those. before you try some on your own. Measure of angle ADB. Now this is a special problem because the orthocenter actually is on the triangle. Now if it's on the triangle, then that means when you take a segment from the corner, the vertex of the triangle, and go to the orthocenter, that house has to be a segment or a line or a ray containing the altitude. So this is an altitude. And this is also an altitude. So what that means is that this angle here must be 90 degrees. So we're talking about a right triangle. So the measure of angle ADB is 90 degrees. Just remember that whenever the orthocenter is on the triangle, you have a right triangle. So measure of ADB must be 90 degrees. Now measure of angle ABD, well, we can just use the triangle sum theorem. So the measure of angle A plus the measure of angle B plus the measure of angle D is equal to 180 degrees. Measure of angle A is 53.1. Measure of angle B we don't know. And measure of angle D is 90 degrees, as we just said. And that equals 180 degrees. Do all the math on that. And you can use your calculator. And I get 36.9. So the measure of angle B is 36.9 degrees. And that's what we're looking for. So 36.9 degrees. And AB, well, we can just use a Pythagorean theorem because this is a right triangle. So this is x over here. We can call that x. And then we end up with x squared equals 4 squared plus 3 squared. And do all the math on that. And x is equal to 5 inches. So AB is 5 inches. All right, so now it's time for you to try an orthocenter problem. I can keep the previous problem in the window if you'd like. And so remember, we're dealing with a lot of 90-degree angles. We're using the definition of altitude to show that some of these angles are 90 degrees. If a segment or a line or a ray comes from a vertex of a triangle and goes through the orthocenter, again, we're told point D is the orthocenter, then it must contain the altitude, and the angles that the altitude makes with the sides of the triangle, they must be 90 degrees. So go ahead and try number 19, and when you come back, we'll do it together. All right, we're back. Measure of angle DEA. This angle must be 90 because we know that this segment goes from a vertex through the orthocenter, so it must be perpendicular to that side. So measure of angle DEA must be 90 degrees. Measure of angle BFD. Same situation. We have a segment going from a vertex through the orthocenter to the other side, so this angle must be 90. BFD must be 90 degrees. So if you got those answers, good job. Measure of angle BAE. Well, we know that this is 36 degrees, and well, let me just show you the triangle we're using. We're going to use this triangle, and it's a right triangle because this angle here is 90 degrees. So I should probably pull that triangle out. This is a 90-degree angle, and this is 36.9. So we're looking for BAE, which is this angle here. We can call that X. So we use the triangle sum theorem. Measure of angle A And you don't have to write the triangle sum theorem if you don't want. You need to show your work, but you don't have to write measure of angle A plus measure of angle B plus measure of angle E is equal to 180. That would just be tedious to have to write that every time, but I want you to see exactly what I'm using here. Let's see here, B, A, and E. So measure of angle A we don't know. I'm not going to call it X, I'm just going to leave it as measure of angle A. So measure of angle B, that's 36.9. Measure of angle E is 90. And do all the math on that. 90 minus 36.9. You can use calculators for this. That's 53.1. So the measure of angle A is 53.1 degrees. So that is BAE. 53.1 degrees. So if you got that answer, good job. Part BE, or the length of BE. So now we can use the same right triangle. We know this side is 10 and this side is 6. And we're looking for this side, which we can call x. So we just use the Pythagorean theorem. 10 squared is equal to 6 squared plus x squared. Do all the math on that. And we have x is equal to 8. So if you got 8, good job. That should be 8 meters, by the way. Try not to forget to use your units. It's one of the most common things students do is they just write the answer. They don't put the units. And they get points taken off. All right, so if you got those answers, good job. We're going to try one more of those orthocenter problems. And we're just going to do a few more problems after that, and then we'll be done. Measure of angle, well, go ahead and try this problem. Remember, we're dealing with a lot of right angles, and this, we're told, point D is the orthocenter. So if these segments go from the vertices to the orthocenter, that means these segments contain the altitudes of the triangle, and there's a lot of 90-degree angles involved. So those segments make 90-degree angles with with certain sides of the triangle. So try number 20. When you come back, we'll do it together. All right, measure of angle CAE. That would be this angle here. Now we know that this is a 90-degree angle, because if this is the base and this, then this must be the top vertex. If you set the triangle on this side, then this is the top of the triangle, and if you extend it down to a segment that comes from the base, then that must be a 90-degree angle, just based on the definition of altitude. So AE or CAE. So this is a right triangle. So I'm going to pull that out and draw a picture of it. That's a 90-degree angle, and this is a 25-degree angle. And we're looking for angle A. That's E. Let me pull this down a little bit. That's B. So we can use the angle sum theorem, and we're kind of running out of time here, so I'm going to just, I'm not going to write out the angle sum theorem. We just know 25 plus 90 plus the angle we don't know is equal to 180 degrees. So now put that on the other side, and we get, looks like 65 degrees for the measure of angle A. And that's what we're looking for. So that would be 65 degrees. If you got that answer, good job. Measure of angle AFB. Well, if this is the base, if we consider this to be the base of the triangle, then this is the top vertex, and if you go down, if you write a segment that goes through the orthocenter, that must also contain the altitude. So this angle, AFB, is 90 degrees. So that is, part B is 90 degrees. If you got that answer, good job. BG, we're going to have to use the Pythagorean theorem, and we're going to use this triangle. We just showed that AFB is a 90 degree angle, so that's obviously a right triangle. And I'm going to write that triangle down here. Don't have much room, but I'm going to try to fit it in. So this is 90 degrees. This is 12. This is 5, and we'll call this x. Pythagorean theorem, x squared is equal to 12 squared plus 5 squared, and x must be equal to 13 kilometers. So BG is equal to 13 kilometers. So if you got that answer, good job. Now measure of angle DEB. Same situation if, I think we already showed that this is 90, so obviously this angle will be 90 also. So DEB is 90 degrees. So if you got those answers, good job. So now we're just going to do a couple additional problems. These problems are going to go a lot quicker, and then we'll be done for the day. We're just going to do a few more problems just to make sure that you got this all down. In the following problems, we're going to find x and y. So in this problem here, we have, I know that we're going to do a few of these problems together, so I know that this is an angle bisector because it cuts that angle in half. I know that this is an angle bisector because it cuts that angle in half. Now, if those are angle bisectors and they intersect at this point, that means this point, this blue point, is the incenter, and it's equidistant from the sides of the triangle. So that means that 2x is equal to 10. 2x is equal to 10. Divide both sides by 2, and x is equal to 5. Now, this segment over here, or this segment, we don't know that that's an angle bisector, but we know that it starts from the vertex and it goes to the incenter. So that actually shows that it is an angle bisector. So that means that y is equal to 38. So y is equal to 38 degrees. All right. So these are much quicker problems. So now on to 22. I know that these are medians. These orange segments are medians. The reason I know that is because they start from a vertex and they go to the midpoint of the opposite side. So, and the reason I know that that's a midpoint obviously is because of these tick marks, right? So we're going to use the Centroid Theorem. This length is 10, so this length must be 2 times 10. That's just what the Centroid Theorem tells us. So y is equal to 2 times 10, which is equal to 20. And this length is half of this length. Or you might be able to say this length is 2 times x, however you want to say it. So x is equal to 36 divided by 2, which is 18. So again, these problems are pretty easy. Now we have, looks like we have perpendicular bisectors. This is bisecting, this orange ray is bisecting this side because we have 4 and 4, so that's bisecting, and we have a 90-degree angle, so it's a perpendicular bisector. And this ray here is bisecting this side because, again, we have 5 and 5, so it's bisecting that side, and there's a little box here, if you can see that, with dotted red dots, that means it's 90 degrees. So that means they intersect at that, if they intersect at that purple dot, that means that purple dot must be the circumcenter. So now we can use the Circumcenter Theorem. The Circumcenter Theorem tells us that the distance from that, and by the way, if you're thinking to yourself, man, this is a lot of stuff to remember, well, again, you should have taken a screenshot of all those theorems. If you haven't done that, then you're pretty much you're probably just sitting there staring at the video and learning really nothing. You got to get a screenshot of these and of the Orthocenter Theorem. Again, you're going to forget some of this stuff. That's okay. That's normal. But you have to have those theorems right in front of you. And you have to have screenshots of that other stuff so you can remember what medians and altitudes and all that stuff are. So the Circumcenter Theorem tells us that the distance from the circumcenter to the vertex x is they're equal for all the vertices. So the distance from the circumcenter to this vertice, which we know is 5, has to be the distance from the circumcenter to this vertice. So x must be 5. And because this is a perpendicular bisector and this is a perpendicular bisector, that means this must be the circumcenter, as I said before. So because this segment goes through the circumcenter, and because it bisects this side, that means y must be 90 degrees. It must be a perpendicular bisector. Again, we don't need a formal proof for that. It's pretty obvious. Y equals 90 degrees. All right. So now we're going to do one more problem together, and then you're going to do 5 more, and then we're going to be done with this video. Of course, you're going to have to do your homework. So now, this segment goes from a vertex to the opposite side, and it's perpendicular to the opposite side because of that red box. Whoops. And looks like my computer is just going to bounce up around like that. It just likes bouncing around for no reason. So this is an altitude. And this is an altitude because it extends from a vertex to the opposite side, and it's perpendicular to the opposite side because that red box. So this is an altitude, and this is an altitude, and they intersect at this point. So that's the orthocenter. Now we know that this segment here, that extends from a vertex through the orthocenter, and so that means that must be an altitude, and these angles must be both 90 degrees. So x is 90 degrees, and y is also 90 degrees. That's just the way altitudes always work. They're always at a 90-degree angle with the sides of the triangle that would be considered the bases. If this is the top of the vertex, or this is the top, or whatever altitude you're talking about. That's just how altitudes work. You don't really have to have much of a better understanding than that. You're just not required to have a better understanding of that for this particular material. Now, number 25, I want you to try number 25. So use your knowledge of perpendicular bisectors and angle bisectors and medians and altitudes and all the theorems that we learned, and see if you can do number 25, find x and y. When you come back, we'll do it together. All right, we're back. These are obviously perpendicular bisectors. And so this is the circumcenter, and the Circumcenter Theorem tells us that this length, the distance from the circumcenter to this vertex, is equal to the distance of the circumcenter to the other vertex. So that means that 13 is equal to 2y plus 5, and y is equal to 4, if you do the algebra on that. And of course, because this is 90 degrees, x must be 90 degrees also. So if you got those answers, good job. All right, try number 26. And when you come back, we'll do it together. All right, we're back. So these are angle bisectors. We have an angle bisector here and an angle bisector here. And so they meet at this point, so that must be the incenter. And we don't know this is an angle bisector, but wait a second, because it starts at this vertex and goes through the angle bisector, that means it must be an angle bisector. So that means that 3x must be equal to 36, divide both sides by 3, and we get x is equal to 12. So if you got that answer, good job. And what is this length? Well, the Incenter Theorem tells us that this length must be equal to this length. So y is equal to 8. Because those are the distances from the incenter because of these right angles here. That means it's the shortest distance from the incenter to the sides of the triangle. So if you got those answers, good job. 3 more problems here. So go ahead and try number 27. And when you come back, we'll do it together. You're going to need the Centroid Theorem for number 27. All right, we're back. So these are medians. How do I know that they're medians? Well, because it starts at a vertex and it goes to the midpoint of the opposite side. Starts at a vertex, goes to the midpoint of the opposite side. Midpoint because we have 5 and 5. And this length is equal to this length. So this median and this median, they intersect at that purple point. So that purple point must be the centroid. So if you have another segment going from this corner through the centroid, it must be a median, meaning x must be equal to 4. Again, I know there's a lot going on here, but as long as you understand those theorems, it's really not that hard. X is equal to 4 feet. And because this is a median, y must be half of 6. So y is 6 divided by 2, which is 3 feet. All right, so if you got those answers, good job. On to number 28. Go ahead and try number 28, and when you come back, we'll do it together. All right, we're back. These are, this one's kind of confusing. These are perpendicular bisectors. They intersect at the circumcenter. So, but we only know that this is a perpendicular bisector and this is a perpendicular bisector. You know, because we don't know what x is. But because this is perpendicular, because this is 90 degrees, and because it's going through the circumcenter, it must be a perpendicular bisector. So 2x must be equal to 2. So 2 is equal to 2x, divide both sides by 2, and we get x is equal to 1. So if you got that answer, good job. Now, the Circumcenter Theorem tells us that the distance from the circumcenter to any vertex must be 3, because it says this distance is 3. So y must be 3 also. So y is equal to 3. If you got that answer, good job. All right, try number 29, and when you come back, we'll do it together. All right, we're back. If we consider this to be a base, well, actually, we need to start here. So if we consider this to be a base, and if that's a base, then this is the top vertex. So notice that the top vertex goes all the way down to a segment extended from the base and is perpendicular to it. So it must be an altitude. With the same logic, if we use this as the base, then this would be the top vertex, which this must be an altitude because it extends all the way down to a segment coming from the base and is perpendicular to it again. So what that means is this is a segment containing the altitude, and this is a segment containing the altitude. So because they meet at this point, that's the orthocenter. Now, because this segment goes through this vertex and through the orthocenter, that means that this must be a segment containing the altitude also, so this must be a 90-degree angle. So y is 90 degrees. And you don't have to think about this every time you do the problem. You just have to use, logic. So now this is a 90-degree angle. Or excuse me, this is a right triangle. So if we take that right triangle out, well, we don't have to take it out, but this side is 8 and this side is 17, so we can use the Pythagorean theorem. So 17 squared is equal to 8 squared plus x squared. And that would be 289 equals 64 plus x squared. Subtract 64 from both sides, and we get 225 is equal to x squared. Square root both sides, and we get 15 is equal to x. So we got those answers. Good job. So that is the class today. If you'd like to take screenshots of all the work we did today, you can go ahead and do that now. These screenshots will help you with your homework and to study for tests. Let's look at the homework. So these are the first 2 pages of the homework. Go ahead and get screenshots. And this 3rd and 4th pages, get screenshots of those. And the 5th and 6th pages. And the 7th and 8th pages. Be sure to do that homework completely and correctly and neatly, and most of all, make sure that you put it in the right chronological order in your binder. Remember, if you don't do the homework, it's a guarantee that you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.